Yes, the first lecture of yes matrix bootstrap.
Okay, thank you, Francesco. And I apologize for my voice. I got some cold. I don't know how yesterday night. So I hope I can make it until the end. So I apologize. So for this set of lectures, I prepared for you like two things. One is more reliable, it's not a book that I will tell you tomorrow how to run some SQL problems. There are some notes under construction, which I now constructed in 1 hour with the help of ChatGPT, but I will improve them in the next days. So everything will be documented. So let me start with some intro, some big picture. And what is this S-matrix bootstrap? So it is a problem that has like two parts. One part is the S-matrix side, which has its own issues. And the other part is the bootstrap side, which has its own issues too. So like two problems, then you combine them together and it becomes a complicated problem. So what we want to do, we want to understand the space of non-perturbative S matrices in full generality, in 100 years or something, but in full generality, and we want to do it using bootstrap techniques. Now, what I mean by these things? So on the S matrix side, there are a few steps that we need to make to define our problem. So we need to define the problem. So the first step is to define what is the set of asymptotic states. Otherwise, you cannot even cope about this matrix. Then the second step is to make some smart choice of observables. Because as you can imagine, this matrix really contains information about all possible scattering processes, and those are infinite, and you have to make some choice of observables. Then you have to tell me how the constraints translate into equations that you can use to study these observables. And the usual constraints that we like to impose are crossing, symmetry, and analyticity. Or its dual version, which is like a singularities. So what I'm saying is that once you pick your asymptotic states, then you can decide what are the observables that you want to study, and these observables will be constrained by properties like crossing and analyticity. And the singularities themselves depend on your choice. So it's like chain 1, 2, 3, and then you go further. And then optional, you can put the fourth point, which is that you can add IR and UV constraints, additional IR and UV constraints, if you are interested in some particular thing. Say you are interested in QCD, and then instead of studying this space in full generality, you want to focus on some particular set. Okay, so this is the S-matrix side. Okay, so once you decide this list of things that you want to do, then you have to set up the bootstrap problem. And bootstrap, it's just like one jargon to mean optimization problems. So what we solve is optimization problems. And optimization problems can be solved in two ways. One is called primal, where colloquially we say that we rule in stuff. And one is called dual. Well, guess what? You rule out. In other words, what you want to do is that you want to rule in the values of some observables given some constraints, or you want to rule out the values of those observables. And then by matching what you rule out and what you rule in, you are sure that, okay, you found a lot of space of observables. Now, there is a caveat here that I want to stress, which is that we can make this program work because today we have like powerful algorithm to solve complex problems. So if we can cast this into a complex problem, then we have solved it in polynomial time. And today we're like powerful algorithms. This is always convex dual, just for you to know. And sometimes, this I will comment later, perhaps you also want to solve like non-convex problems, which are NP-hard in general. So in general, you can solve non-convex problems, which are very, very hard. This we don't know how to do it efficiently. Maybe with neural networks, there is like a neural network, a smart way to explore the space of non-convex problems. And the dual version of a non-convex problem is always convex by definition. Hello? It's always convex by definition, but it might be not optimal. Okay, so this is the situation we have now. And well, in this set of lectures, I think I will only explain this part here, the primal, and how to rule in, and of course using convex methods. Perhaps I will briefly mention some dual bounds. And today the introduction will be about, well, we will start to discuss this part. So how to define the problem. Okay.
Sorry, can you say again what is not optimal? I missed it.
Not optimal just means that the dual, even for non-convex problem, is always convex by definition. But then, you can imagine that if you like some banana shape and then you take a convex out, then what you exclude is like smaller than what you should exclude. Okay, so is there any question? Otherwise, I will start filling this list. Okay, so even to start, we need to pick some asymptotic states. So let's start with point 1. That means that we need to choose like some space-time. And for me, like V will be like V minus 1 plus 1. So this is like the all the dimensional space-time. And then asymptotic states are easily classified using the Poincare group. So this is something that you already know. That you can, let's say that, for instance, for a particle with mass, so with mass different from 0, I can also classify the state with the energy or the momentum, let's say, some helicities, if they are spin, and internal quantum numbers. So this you can always do. And how you see this? Well, if you have like some time-like momentum, you can boost to center of mass. Then there will be like the mass here, and then 0, 0, 0, 0. Right? And this vector is like invariant under SO d minus 1 rotation. This is called the little group. A representation of SO d minus 1 will tell you in which representation is this state. And then the lambdas depend on how many of this polarization you can have. For instance, it equals to 4, which is what we will mostly discuss. This is just SO3. And then we know that we have the usual speed. So we have the usual J equals 0, 1/2, 1, and so on. And each one is multiplied to J plus 1. This is standard. Now, if the mass is equal to 0, so if the mass is equal to 0, so then can I write down here? You cannot see. So if the mass is equal to 0, then we cannot boost the particle at rest. We have to pick some reference vector. So for instance, you can here there is 0, here there is 0, you can choose this reference vector, this downward direction. And then the group here, the little group is smaller because you can only rotate around this direction. So like S of d minus 2, but you can pick many reference vectors. So there is enough. d minus 1. It's like the choice of the reference vectors. And usually, when we find scattering states, we don't care about the, let's say, this R acts on your state. Usually, it's always like the, identity representation. But for instance, there are these weird continuous spin particles that we recently discussed in literature, and they are when you care about this part. But usually, in general, you only care about the S of d minus 2. And then it means that for dimensions, again, you have the usual helicity, right? For usually, you will have like H will be like 0, plus minus 1/2, plus minus 1, and so on. That's the usual. Okay, so these are the choices that you can make. Except from Brando-Bellard series, the only one that is brave enough to study these continuous spin particles, we will not do it. So we'll like stick with the usual irreducible representations of Poincare, Unitarity reducible representations. And well, this is the first step you have to take to formulate the bootstrap problem. Choose your asymptotic states. In these lectures, I will only focus, my choice will be, let me put it here, my choice is to pick mass equal to 1, units of the mass, J equal to 0, so scalars, D equal to 4, but I will keep some formulas in general D, and what else? Some Z2 field symmetry, so Z2 field. So I will even make them even under Z2. Okay, so this will be the choice. Now, what are the observables? I can start erase this part. Let's look into. And the observables will be, in general, the M2M S matrix elements, in general. And I remind you they are simply defined by this overlap. When you have, like, for instance, this is out, there's some out state, P1, PM, and then some in state of part with moment, sorry, in state of particles with moment Q1, Q1. So this is usually how you define. But in general, you also like form factors. And form factor is the same thing when you here add the local operator. P1, PM, then like some local operator, we can put it at 0, for instance, and then Q1, Q1. In. Now, in general, in local quantum field theories, these are both good. But in gravitational theories, all the S matrix elements make sense. So in that case, we cannot have like a diffeomorphism invariant local operators, and therefore the S matrix is the natural observant. But if you're in QCD, we can enrich our set of observable by plugging local operators in these matrix elements and measure what are called form factors. So this is in a very generally the objects that we want to study. Now, for this set of lectures, again, I will focus on some very specific process, which is only 222. Only. And the reason is very practical, and I will tell you in a second. And okay, so let's say something about this 222, why we like it. Well, first of all, it's like the first, I mean, the scattering, let's say, process we can study. And okay, here there are some okay, here there are some steps that I'm not gonna go into details because they are very pedantic. Because here from in and out state, you want to go to the interaction picture, then you define this matrix as the the operators that makes this overlap in the interaction picture make sense, and so on. But so without avoiding this pedantic part, so what I want to say is that here this S, we usually like to split it in some identity. plus interacting part, IT. So we usually make this splitting. Then if we make this splitting, we get this nice free piece, some disconnected piece, plus, so let me perhaps erase so blackboard it's more clean. So there is a plus with the, let's say, the interacting piece, which is what we are probably more interested, which yeah, I will call it, let me call it for now SC P2, P4, P1, P2. And now let me make a comment about this piece. So this piece, usually, if you don't have long-range interactions, this becomes just delta function. This means that particles at large impact parameter can be clusterized, they can be separated, and this thing just gives you delta functions. So this thing, if you don't have long-range interactions, become some S11, which is not defined in the set, it's just a normalization of the relativistic states. P4, P2, and then there is plus P3, P2. Then we stay with P4, P1. And then plus the connected piece. And the issue with long-range interactions, which is also the issue that we have with gravity in 4 dimensions, let's say that it's still we want to study, is that this part here, this factorization is not very nice. Those particles cannot be clusterized, and you cannot claim that that is some of delta functions.
Can I ask you something? Maybe it's not where you want to go, but like, what is the obstruction to just say that in any case that's a normalization? You're saying it is a normalization, but the two-particle state cannot be factorized in one particle state. That's the problem.
Yeah, this because you see here what I'm saying is this overlap between two-particle states that factorize in. So I have to tell you what is this S11. This S11 of P and Q is just the usual delta function. It's like 2 times the energy. P, there is like in the dimension P pi to T minus 1, some delta T minus 1, P minus Q, and that's it. So you see the particles basically fly through without talking to each other. And this you cannot claim if you have long-range interactions. And for instance, yeah.
If you're long-range interaction, can you define asymptotic state?
So that's the point. Like, for instance, how you define asymptotic states. So you can, for instance, talk about Coulomb eigenstates. If, like in relativistic quantum mechanics, if you solve the problem exactly, then the Coulomb wave functions are the object that you want to scatter. But in general, you always start from plane wave, let's say, and being agnostic, and then construct these matrix elements, and then check what happens. Then what happens, we'll find a contradiction with the definition of, free asymptotic states, is that this thing will carry some dependence on the energy. It will be like some non-trivial function.
Okay, so basically, if I want to study, let's say, scattering between electrons and then dressing electrons with the shell of photons, this would become a well-defined, more or less a well-defined asymptotic states, and then I have also cluster decomposition or not?
Then, so this is like an open issue how to do it, but the dream is that once you do it and you strip this dressing, what remains can be clusterized in the same kind. That's the dream. But nobody knows how to do it non-perturbative. As far as I know, unless the celestial community already solved the problem. So, probably the celestial collaboration. Okay. So now what about, so this was just a comment. I mean, I don't want to really go into that, but to say it's like an open problem that I'm very interested, and it's, yeah, because we want to bootstrap gravity in 4 dimensions, and we cannot do it. I think we have like some nice understanding of this part. Now, The connected piece, so these are just delta functions. So these are just delta functions. If we can clusterize particles apart. And this part, which is the interesting one, or this part is usually, we put some delta function outside, 3 plus 4 minus 1 minus 2, and this multiplies the scattering amplitude T. So this is the object that in the end we want to start, because all the rest is trivial delta functions and pi factors. Okay, so what is nice about to do scattering is that, as I'm writing here, there are only 2 variables. So you start with the many momenta, but in the end it's function of only 2 variables, SMT. So what are these SMT? They are usually defined in this way. So you have like 4 particles, one momenta P1, momenta P2, P3, and 4. Then S is P1 plus P2 squared, which I take it to be positive. And then T is P1 minus P2 squared, which is negative, and U is P1 minus P4 squared, which is also equal to 4 minus S minus T by the element conservation, which is also negative. So these are the 3 variables, and only 2 are independent. And this is the reason why to do scattering is nicer, because it has like the least number of variables. And they are identical particles, so this relation is even linear. You cannot really make it nicer than this. Okay. Now, it's also useful to introduce some other variables. So, for instance, this process, you can go to the center of mass of the incoming particles, and then you can put them on some axis. And then this process is planar, and the outgoing particle must go in this way, and there is an angle theta here, which is the scattering angle. And therefore, we can also parameterize the, let's say, the independent variables with the scattering angle and energy, or momentum. So, for instance, T will be 4 minus S divided by 2, 1 minus cos theta. So that's some linear relation. And U, there is a plus. It's just an notation. Okay, another observation perhaps that the amplitude, okay, this will come out later, but the amplitude T is dimension 4 minus D in energy. So in 4 dimensions, it's also nice observable because it's dimensionless, while in higher dimension, you have to introduce some scale. That's still to say. And that's it. So this is the problem we want to start. Now, since the particles are identical, and here I just pick some choice of momentum. For instance, I claim that these are the particles that go in and these particles that go out. But I can also look at the process in some other channels. For instance, I can imagine that I look this process from this side. And then P1 and P3 go in, and P2 and P4 go out. So if I do it, if I look it from this point of view, then this means that this is what is called a cross process. And when you perform crossing, this SP and U swap, in the sense that when I look the, let's say, scattering process, when I take P1 and P3 that go in and P2 and P4 that go out, then T becomes positive. So, okay, let me erase some. This is not very useful.
So S you wrote positive, but you can also write bigger than 4, right?
Yeah, positive and bigger than 4.
Okay.
So if you go to this, if you look it from this way, then T will be greater or equal than 4, and then U negative, S negative, and then you can also look it in this other channel U, and then T. Okay, this is like you can imagine. And now the question is, and this is like one of those questions people ask, is that how can we connect these channels? How can we jump from this S, which is going to contain 4, T negative, U negative, from this other channel? And this may seem an innocuous problem, but it's a formidable problem that was solved in the 64 by these people, B.G., Broseps and Glasser. And doing some crazy gymnastic, taking correlators, time ordering, and analytic continuations, and so on, we could manage to prove that you can analytically continue to all these channels. And to do this analytic continuation, already the name tells you, entails the need to take the momenta of the particle and make them convex. And this is the reason why we want to really go to the complex plane and discuss this scattering amplitude not just as a function of real energies and angles, but also like as an analytic function. Because in this way, it becomes like a single object that connects these three channels nicely. And analyticity, as you can imagine, gives you like further constraints than just being a real function. Yeah, the fourth is defined by mass shallowness. So, yeah, thanks. Okay. So this is so we have to be complex. And if we go complex, it means that we have to understand a little bit the analytic structure. This is where singularities start to enter into this game. So let me erase something. Probably this delta functions. Okay, this delta function is just relativistic normalization. T is this one.
What now happens to the space of phase?
Sorry?
The scattering angles, what's happening now in space of.
Ah, right. There will be like a different scattering angle. And they are non-linearly related. Theta S, theta T. Yeah.
Maybe it's useful to know if, regardless of the general setting, in examples, you can always do this complexification or.
Yeah, in the sense that this complexification, you can always do it. There might be obstruction on how far you can go. And the obstruction depends critically on the values of the mass. Now, if you have like the scattering of all these scalars, there is no issue at all. But if you start to add other particles to different masses, then that's where things become messy.
And there are those people who show that thing assuming their own spectral representation or something like that, or did you make any assumption on spectral representations of this thing? Because I'm not sure.
Well, it's from the white line axioms, as far as I know. So you have like, spectral densities, you have temperature distribution, and then they started from LSZ. So you want to be LSZ or some T product of operators, scalar operators. And then each component of the T product is like some correlation function, which has its own analytic domain. And they were, they were performing analytical, they were analytic extending each correlator separately, gluing together using the edge of the wedge, then keep gluing edge of the wedge and and then in the end, claim that when you perform LSZ, you end up with some domain. So that's the tools that they use. It's combinatorial, but the details are excruciating. I never understood. But yeah, it's quite general. They were careful. Okay, so we have this ST. So let's draw some picture to understand this analytic dynamic properties. So it's useful to introduce the Mandelstam plane because we have this S plus T plus 2 is equal to 4. triangular relation. So we can put the three variables on a plane. So this is S, this is T, this is U. You can draw it like this nicely. This is the T equal to 0 line. This is the T equal to 4 line. And this is the S equal to 4. And this is U equal to 4. Okay. And now the regions, the various, let's say, regions where the different scattering are here. So this would be the S channel region because S is greater equal than 4 and T is smaller equal than 0. Then we can use follows. So this will be S, then T will be up here, and U will be down here. And now I'm going to justify in a second that the region that is like inside this triangle, it's called the Mandelstam triangle, and that's where the amplitude is, for this case, it's real. Here the amplitude is real. And all the singularities, they lie basically after the sequence. So what the singularities go. So what we can do, some nice thing to do that we found useful is to expand the amplitude around what we call the crossing symmetric point. So this point is the point where S is equal to T equal to U equal to 4/3. We can expand. It admits an absolutely convergent expansion. And we represent this amplitude as this series, sum over n and n, some coefficients C and n. Now, let me tell you what are the sigma and tau. Sigma and tau are just cyclically invariant polynomials, symmetrically invariant polynomials. So this would be S minus 4/3 squared plus T plus U. And tau will be the degree 3 polynomial. T minus 4/3, U minus 4/3. So if I organize the expansion in this way, these C and N coefficients are in there. So it's just a nice way to parameterize a function which is invariant under permutation. And this C and M, it's what we call S matrix data. So this is what we call S matrix data. And they are nice for at least two reasons. One is that, of course, if I specify all the C and M, I can resound this series, and then I can analytically continue and define the whole amplitude. And the second reason is that they are bounded. They obey two-sided bounds. And the goal of the bootstrap in general is to understand what is the geometric space of this CNN. So you see, in other words, what we achieve by introducing these coefficients is that we discretize this space. So we have a function which is an analytic function of two complex variables, that it has a lot of degree of freedom. So we have this old TST, and we trade it for a set of discrete coefficients, C and F. And this is the objects that we want to understand the geometry. And these objects, they will define what we call the amplitude space. This will be the amplitude space. And this space will be shaped by unitarity, which I haven't specified yet, crossing I already introduced, and causality. It's the last ingredient that we will do. So these two ingredients, you put them together, they demonstrate the CNM and then define the amplitude space. So this is the problem. Yes.
So if you have these coefficients with very high precision, how difficult is it to actually go into a physical region by analytic continuous?
Well, I'm talking in abstract.
Okay.
You need all of them.
Yeah. So if you have them numerically, that's hard.
Yeah, it's hard. So what we do actually, but okay, there is like some, there is an answer to this question which will come soon. Is that what we can do with the bootstrap is that we can find the boundary of this space. And at the boundary, we can reconstruct the amplitude uniquely because it's obtained by solving an optimization problem which is convex. It has a global optimum, and then you determine the full amplitude. So you can, for instance, if you give me like C10, if you don't give me all the other CNN, I cannot tell you anything. But if you maximize, say, C00, then this fixes all the CNN, and actually then we can actually recover the analytic configuration. And this actually will be the strategy. So we will reconstruct candidate amplitudes by solving. Yes.
What's the motivation of this parameterization, this particular parameterization? What's the reason you're using this parameterization model?
It's a nice parameterization because since it's around an analytic point, this CNM obey two-sided bounds. So they are bounded from above and below in general. And that makes the space compact and easy to start numerically. For I give an example. For instance, if you expand the threshold, let's say, then you will have like the usual threshold expansion, and that's not an analytic point. So in general, these coefficients could be infinite. So for instance, the spin zero scattering length, if you put a Polar threshold, that can go to infinity. And that you can do it numerically, it just becomes a little bit more complicated. So this infinity to be careful. Yeah, this is the only reason.
So then the sigma n functions, what are those?
No. They are just symmetric polynomials.
What are
Okay, sorry, that's what it is. So
Yeah, they're just
symmetric polynomials and that.
Yeah, of degree 2 and 3.
Is there a reason why, so if I understand the different monomial as the new monomial,
Yeah.
the difference of exponent can jump only by an even number with this parameterization? Like when I expand that?
U is minus.
Okay.
Yeah.
So you see what I'm saying? But the jump is by 2.
Yeah, exactly. So because the thing is that since we are like moment conservation, you don't need to add this this polynomial because it's always a constant. But in general, these are in general, if you do it like for a higher point function and so on, these are just the the generators of the algebra of symmetric polynomials modulo your global symmetry of choice. So you can make it formal and as you want.
In principle, you could have used also partial waves, I guess, but that's the less efficient numerical or something. Or
Again, yeah. Let me. I will go to partial waves soon because we want to talk about unitarity. But I mean, the thing is that this expansion is very nice because it's like an analytic point. It's real for identical scalars, absolutely convergent, and convergence in a polydisk. So in ST, but it can also it can be analytically extended in STU because it's like domain of homomorphism. There are all these concepts. I don't want to go too much into them. But for instance, there is a nice picture that the projection of the polydisk is this region. I didn't want to draw, but the region of this. Some weird thing like this. It converges. The projection is this one. That is some nice region of convergence. Anyway, it will clear. I mean, it will be more clear soonish in 10 minutes. Why I really like this coefficient. And there is also some subjective principle here, some anthropic job. Okay. So let me accelerate a little bit on this part because it's just unitarity. So I don't want to regret unitarity or anything. Some things are in the notes and maybe it can be an exercise. So well, yeah, perhaps I can erase here. So next time I will tell you, next time that you, I mean, this is like a warm up. So next time you will be warmed up already. I will tell you a bit more about analyticity, what we know. But for now, let's only discuss unitarity, and then I will show you like an example of amplitude space to give you a teaser. Okay, unitarity, I remind you something extremely basic. So it comes from this fact that S is a unitary organism. And then it stems from the fact that S, since we can clusterize particles, we can split it nicely into 1 plus IT. And then what we like to do is to, okay, let me do this step. I know it's a bit trivial, but let me do it. So when I write this equation, and then this equation, if you do the algebra, implies that T minus T dagger is I T dagger. Then we take this equation, we bracket with some states. So let's say I take final here, an initial state here, I bracket this expression, and this gives me the relation that you perhaps saw, where this T E that goes to F, you understand, it's like into final state, minus the dagger becomes a star, and then since there is dagger, I have to exchange F and E, so I get F that goes to E. This is equal to E. And now there is a sum. There is an integral of the following invariant phases, which I will write schematically like this, but it can be very explicit. It will make some very explicit. And then you have T and goes to F, and then T star E that goes to F. And this is the most general unitarity equation. And then if F is equal to E, so if the final state is equal to initial state, you have the optical theorem that you all know and love, which tells you that, well, here you get E, same initial and final. T minus T star is the imaginary part. So it becomes 2 times the imaginary part of T, E that goes to E, equal the I can drop it, and then becomes the sum and the integral of stuff which are just positive. And this is the usual reality when the imaginary part is positive. Unitarity is a bit more, because this equation is also telling you that this right-hand side is actually a Gram matrix. So it is not each other is positive, but it's semi-definite positive. It's like more general. So, and we want to make this very explicit, because here you cannot really see it. You have to think a little bit to see it. So that's semi-definite positive. So how we make it explicit? We go to a smarter basis. And we go to a basis in which this integral diagonalizes. And that's the partial wave basis. So the reason why we go to partial wave is that because we want to diagonalize this integral and make it become an explicit sum of stuff that you can recognize to be positive. You see it right away. So, okay, let me erase this part, save the drawing. So next time you don't use these partial waves. Lorenzo will be happy now. So let's do it. Okay. So, well, I will not make it too long this story, but so in 4 dimension. So let me, since we are in equals to 4, let me use 4 dimension. They are just defined by integrating with respect to the Legendre polynomial. So it's a simple integral in the Z. Then there is like Legendre Z, and then this T of S and T of S and Z, where Z is cos theta. So here instead of T, you have to plug 4 minus x by 2, 1 minus Z. Then you relate this integral for each S, and this, oh, sorry, I forgot J. And this gives you the partial waves. Now, if we introduce these partial waves, that you can also think that as like 2-particle state defines a straight line, and therefore this like invariant under rotation, and therefore, like you can imagine that the actual state that you want to take, a state which are eigenstate of the total angular momentum J, there will be like some M like this, and then the amplitude by the Wigner-Eckart theorem will become diagonal in this space. So this partial wave, if you want to write them in some matrix notation, just to understand a little bit, are just this matrix elements. On these nice states, which are like angular momentum eigenstates, like this, and then normalized by this thing. J. And this is what this proportional to this Fj. So this is where they come quantum mechanics. We go to like a good state of base, which is not just the moment. Okay, anyway, but once you do this, then the amplitude becomes nice, because then the amplitude admits like an expansion in these partial waves, which in 4 dimension it's just there's like a 16 pi, you say 32 pi, then there is like Fj of S, and then here there is some Legendre of cos theta. And if you plug this representation inside this equation, this one is of course just the sum of these partial waves, but the magic is that the integral diagonalizes and also becomes a sum. And you can write unitarity as like a scalar equation for each partial wave, and not like some complicated integral. So it becomes just a relation that 2 times the discontinuity that becomes the imaginary part of the partial wave, Fj, is equal. So in any dimension, that would be like -3 divided by 2, but I said in 4. So like the square root of S minus 4 square root of S. Then there is Fj of S squared plus dot dot dot. And this dot 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 are negligible when S is greater or equal than 4. So the S is smaller or equal, well, between 4 and the first multifactorial threshold, which in our case is like 16 per square. And they are negligible, but in general they are there, but they are positive. Therefore, we can always say that this inequality holds.
Sorry, a question. In the sum over n in the unitarity, we are restricting to particle states, or
no. So here you are summing over all the n particle set.
Yeah, but in this, when I want to apply this thing, like this rewriting in terms of partial wave, we did it only for the 2 to 2, or we can do it over 2.
No. Well, we can do. I mean, imagine that you bracket with these states now. If you do it, then this becomes this side.
Yes, that's right.
The 2 to 2 part of this integral becomes this.
Okay.
And then the n particle integral will become let's say, so what you will have here, instead of T, you will have like matrices now. So because plot diagonalizes in total angular momentum sectors. And this matrix is, of course, like a symmetric positive. So then this thing will become positive. So you can show that each contribution easily is positive. But of course, in the 2 to 2, it will enter a sum and integral of the possible. Yeah. Like when you have this kind of adapter. Okay, so the important point is that, so let me stress that this becomes like this, an inequality. This inequality is always true. So it's always true. And the fact that it's an inequality makes it a convex constraint. So it becomes convex. And if it's convex, we can use our powerful algorithm that people developed in the 90s, and we can solve it efficiently. And that's what the bootstrap does. So this is like the central form. Okay, so next time I will go into the details. I will explain you how we go from this abstract constraint into some practical implementation, and I will show you how to get bound, and there's a notebook that you can run, and you can have fun.
Andrea, what we've written is only for final states and initial states. Those you don't put in
Sorry?
in this matrix. The F that you're using there,
Yes.
it's just for elasticity. Initial and final states are the same.
This is why
You don't have the partial wave squared. You have F. It's not diagonal.
so. Yes, yes. Here I'm considering the scattering by identical particles.
No, I don't know that. No, yes. Okay, yeah,
Only one.
Only one, only one.
Only one part.
Yeah.
No, I'm confused because you got internal numbers at the beginning, so
Yeah.
there are no internal numbers to differentiate.
No. At some point, I wrote here. Well, it was at the beginning.
That happens in differentiates. So that's one of my problems. So there are no really internal numbers. All your variables are identical. That's it's not.
Yeah. Exactly. There is no internal quantum number. So otherwise, I totally agree with you. This can become matrices. You can try to legalize in, yeah, absolutely. So it's really the simplest possible example. Okay, then there are some nice, there is like some other nice representation we just mentioned, but I really want to draw a picture. So I will try to be fast. So we like to combine this F with some 1. So we like to do this. We like to define Sj, which is 1 plus R. This factor here, which is like a space factor. Sometimes we call it a rho. And you put Fj, and then this inequality becomes simply the fact that the probability is constant. So if you write it in this way, then this inequality becomes just the fact that the probability, this Sj is not equal to 1. That's like a beautiful way to see it. And then usually it's also useful to parameterize this Sj in terms of a phase, which is called the phase shift. So usually it's nice to parameterize it like this. It's very hard, it's like nonlinear parameterization. And this delta J contains all the information. And in particular, the imaginary part of delta J, because of unitarity, must be positive. Let's see. And then you can define, for instance, here e to the minus 2 times imaginary part. Often you can call it eta J, which is like the elasticity or sometimes elasticity. So these are all the same thing, same information, we call it different things. Okay, so we will go into these things later, for sure. Now, let me give you an example of amplitude space. So let me give like some example right away, and the next time I'll tell you how we do it. I think it's time to erase this. Okay, we'll erase it.
What is the main motivation behind writing as a phase shift? Is it from WPV?
Yes, there is some, there are many reasons. One, for instance, is that if you go to the current limit, right, it's the amplitude exponentiates, and then the phase shift becomes just that level amplitude, and then goes into the equal representation. You have some WKP, approximation. Exactly. But it's also nice instead that from the phase, because usually, experimentally you get absolute value, because you measure cross section, absolute value, and then with some effort you reconstruct the phase, and then the phase is what has like some physical information, and that's well, we will discuss these things. Okay, the example. So we have this CNN. So what we can do, and that's like the notebook that I prepared for you. You can take C00, C10, which are the first 2 coefficients, that you can think of them as like lambda, phi to the 4 interaction, then d4, phi to the 4. If you want to have some Lagrangian handle, no, you can imagine as like this. Then the space of this the space of this S matrix theta is given by this convex shape. So there is some part here, there is some part here, and then it connects like this. And what is contained here? This is like the full amplitude space. So all four-dimensional or non-perturbative four-dimensional scattering amplitudes of 2 to 2 identical scalars is the whole title. It will be contained inside this region. This you can find it using the S matrix. And then what I will tell you the next times is that we can study the theories of the boundary, because the boundary is obtained by maximization problem. When you maximize, you fix all the coefficients, the solution is unique, so you can study. And this space give you it has some interesting structure. For instance, here there is a free theory. This is free theory. Then here you have like theory which can be approximated by something that we call a threshold bound state. This is something 1 over square root of S minus 4, minus 4 plus 1 over square root of U minus 4 plus dot dot dot. And here in this cusp, you have something that we call the Frost amplitude. And this is the mostly interacting amplitude you can find in this space. And then you can also study these phases of this space. You can ask, what kind of theories do I have here? And then here, you have some, because this C00 actually is minus lambda 5 to the 4. So this is the side where lambda is positive. So here, like some lambda 5 to the 4 EFT, which we know that alone cannot be, for perturbation theory, we know that alone cannot be the whole story. And actually, the bootstrap spits in amplitude that looks like lambda 5 to the 4, but then eventually has like a higher spin sector, which is strongly coupled. Higher spin, strongly coupled. And this phase goes from this point to this point. So if you go this A, this C, this is the AC phase, where you have this situation. Then on this side, something fun happens. Because on this side, you don't have phi only, but you have also threshold states. So you have like a spin zero particle that sits at m squared equal to 4. Then you have like spin 2 particle at m squared equal to 4. This is the threshold. And then you have like a higher spin states. On all this side. Here you have some large N phase. So here there is some large and kind of decoupled phase of the side spin sector. And then finally, in this AB, you have what we call asymptotically free scalars. There are some asymptotically free scalars because the amplitude T goes to 0 at infinity. And they are described by some weird minus lambda 5 to the 4 effective field theory, which, as also Lorenzo mentioned, I think at some point, it's very unstable unless you put some higher things. But the bootstrap constructs like a solution approximate is like minus lambda 5 to the 4 in the HeI in all this case. And that's it for today. So next time, so can I conclude? I don't know. I think I'm 1 minute for that time. Sorry. So next time I will tell you how you can construct this space, and I will explain you how to use the notebook if you have SDPP, of course. But then, okay, if you want some help, you can install it. How you do it in practice, and then probably in the third lecture or something, I will give you some prescription of how can we learn all these properties. You know, when I tell you this, like what kind of analysis you can do to understand this kind of properties that I mentioned here. So I will tell you like some tricks, some observables, something that you can study, And then on the plan for last lecture, I'd like to give you some overview of applications to QCD. Maybe it's more interesting. So, thank you. Stop.
Are there any questions for Andrea?
So you only have one trace for the software for the amplitude, that's further down, that's the only one. The only one.
So,
That's why it stands.
so dispersion amplitude is the amplitude is like the biggest cross section.
And
No, two languages.
rolling.
In some integral sense. In sense, as an integral, this so if you smear the cross section up to S, this faster amplitude or some slight modifications for some is the biggest cross section. And then as you smear it and you go to astronomical energies, then it's really this amplitude. So you can think of it as like the amplitude that maximizes the integral of the cross section up to asymptotically high energies.
Figure out the cross section over.
S, yeah, over the energy. Yeah, exactly. And for instance, it's hard to extract numerically the actual value. Yeah, the value in sense. But what we did is that we did an improvement to the first bound in the sense that we showed. Actually, it's an improvement as a result of Indurain and then Martin, in which
I was contrast.
yeah, exactly. So we basically use the same Indurain observable. But Indurain was related to the spin-to-step length, which is observable, but it's infinite. It can be infinite, so you have to fix it. But if you relate it to one of these S matrix data, which are finite, then you can combine numerical bootstrap input with some analytic derivation and derive some finite energy rigorous bounds on the cross section. It's not asymptotic; it's really tolerant, and that must be satisfied. And then we can also expand it, and by expanding it, we also obtain the sublimit corrections to the Flassard bound, which are like precise sublimit corrections. Yeah, in the sense, but now since we have like but it's the same, strategy is the same, but we could use the numerical bootstrap to go further, to make it precise, but you need numerics to. Yeah. Well,
Okay, there are more questions. Let's thank Andrea again. So let's have a break of 10 minutes and we resume at 3:15 with the talk by Arturo. If somebody wanna go upstairs in seminar 3.2, there is still something to eat and but please come back at 3:15. Yeah.